Okay, so again, we're in chapter 12. I'm just doing like the SparkNotes version. And we're starting with this definitions at the beginning, vocab. Some of these you already know. So the first one, a segment whose endpoints lie in a circle, that is a chord. So a chord is a segment whose endpoints lie on the circle. If I'm looking at like this as a diagram, can someone give me an example from that like diagram what a chord is there? It's an example of a chord. Caleb? Which one? CB. That's not a chord. Missing a little bit. Donna? Say again. BE counts as a chord. Billy, did you see a different one?
No, I saw the same one.
Anyone else see a different one besides BE? Drew? BH works. So Caleb, the reason yours didn't work is it didn't go all the way through the circle. So you got to go all the way through the circle. So BE or BH works. And I want us to think of these as segments because they end. Okay. Now I'm going to teach you two new things that you didn't know before. These are two different types of lines. One is a line in a plane of a circle that intersects with only one point on that circle. And that line is called a tangent line, or a line that is tangent, is a tangent line. So an example of that is like DE, this line right here. D, you can call it DE, DG, GD, EG, whatever you want. Any combination of those three letters you can call as a tangent because it only intersects at this one point of E. So I'm going to come up here and I'm just going to call it DG. And it's a line, so put arrows at the ends of your lines. The next vocab word goes with this one. It says the point at which the line intersects with the circle. It's called the point of tangency. I think it's kind of silly when you have like definitions that are like almost the same thing, but like one's a line and one's the point of the line. But that's all right. We're going to call it the point of tangency. And that is point E. That's the point where the line intersects with the circle, and it's exactly that one point. And then the last one, a line that intersects the circle in exactly 2 points is what we call a secant. So secant is a new word. We'll use it more when you guys get to trig in a couple of years, but secant is another name of a line that intersects 2 points of my circle. So let's pretend that, like, I don't know, BE, like we called that a chord, but let's say it extended out and had arrows at the end. We could call BE, the line BE, with arrows at the end to be our secant line. EE is our secant line. All right, cool? All right. I know we just used that diagram, but we're going to use it again. And this time I gave you segments and I want you to tell me what they are. We have options of a chord, a secant, a tangent, a diameter, or a radius. So we're going to use those words to describe these segments. So we'll start with HC. What is HC? Caleb? That's the radius. Very good. So this is a radius. It's a radius because it goes to the center of the circle and its other endpoint is on the circle, but not both of its endpoints are on the circle. Very good. All right, let's do BE next. What's BE? Just a segment BE. Billy? A chord. Very good. That's a chord. Since it's a segment, it ends. It's not a line. And it intersects its endpoints are both on the circle. So it's a chord. All right, and then last is BH. Caleb? It's a diameter. Very good. That's the word I'm looking for. There's another word we can also use, though. What? I think you said it. What did you say, Jackson? Not radius. It's a diameter. You also can call it a chord. So a chord works because its endpoints are on the circle, but it's a diameter because it goes all the way through the circle and through the center. All right. Next, I've got DG and AF, and both of those are lines. Looking at our words, is a chord a line? Does a little chord go on and on forever? No. What about a secant? Is a secant a line? Yeah, we just learned that. What about tangent? Is that a line? Yes. What about a diameter? Is that a line? No. What about radius? Is that a line? No. So I just went through and I said, okay, what even counts? So the only two things that will work for B or D are secant and tangent. So let's go look at the picture, decide which one is which. So DG, oh, come back. DG is this line right here. Is this tangent or secant? Is this a tangent line or secant? Tangent, very good, Billy, tangent. It only hits at one point, point E, so it is a tangent. And then what about AF? If AF was a line with arrows at the end, what would that be? Caleb? It's a secant, very good. So see how it connects at 2 points? It crosses a circle at B and at E. So since it goes through 2 points, it's the secant. All right, now for our favorite, sometimes, always, never. That being said, I talked to my other class today, and this morning I did PLC with our geometry teachers. We are not putting sometimes, always, never on your final. So I hope that's a nice sigh of relief. The reason is honestly, we just haven't really done it a lot, right? It hasn't been super useful in like chapter 8 with our special right triangles. It's like we're kind of using it here, but it's not as relevant as it has been. We used it a ton first semester, but not really now. So we just didn't think it was like super useful or fair or even really helped us assess your knowledge. So we're not going to put that on there, but we are going to do a few now. So let's do it. Okay, first one, a diameter is blank a chord. Is that sometimes, always, or never true? Sometimes. Can I move to always or never? I'm going to say it's always. Why is always true? Why is the diameter always a chord? What does it mean to be a diameter? Jackson? Yes. And a diameter specifically goes through the center, right? Its endpoints lie on the circle and it goes through the center. And then a chord, by definition, is just have endpoints on the circle. So a diameter is just a special type of chord, which makes it always a chord. What about a radius? Is a radius sometimes, always, or never a chord? Never. Good, Melissa. Never a chord. Because it never goes from endpoints. Its endpoints are not on the circle. One's on the circle and one is the center. A chord is blank a diameter. Jackson? Sometimes a diameter. Because I went the other way around, so a diameter is always a chord because a diameter is a more specific thing. A chord could generally just be anything that has endpoints on the circle. It doesn't have to go through the center. And then a tangent is blank a secant. A tangent is blank a secant. Yeah? Never? Why?
Because secant is a line that intersects 2 points of the circle, and then a tangent is only one.
There's no way for us to do both, right? You can't intersect at 1 point and also intersect at 2 points. Like, that's not how it works. So it's one or the other, so they are never the same thing. All right. Nice little brain warm up. All right, now we're going to do a theorem. We're going to do some practice problems on that theorem. We're going to do another theorem. We're going to do some practice problems, et cetera, and on for all of this stuff. So we're going to see how much of this we can get through. And then when I think we're at a good stopping point, I'll stop us and we'll work on our homework. So we will not hit all of this today. The first theorem we're going to talk about is talking about tangent lines. So I had to teach you about tangent first before we could do anything else. It says, if a line is tangent to the circle, then it is perpendicular to the radius drawn to the point of tangency. Okay, so I've got this picture. I've got a circle, and I see that line L, that's this line right here, is tangent and intersects at just P. And if it is tangent, then I have a right angle between line L and then the segment PQ. So because I know it's tangent, then I know that it's a right angle. I can also go the other way. I can also go backwards and say, if I know that it's a right angle, then I know that L is tangent. So if I already know that they're right angle, then I can assume that this line is tangent to the circle. Okay, I got a couple blanks to fill in. This one says if L is tangent to circle Q at point P, then L is perpendicular to PQ. So I'm starting with if it's tangent, then there's perpendicular, then there's a right angle. If I can also go the opposite way and say if they're perpendicular, if there's a right angle, if L is perpendicular to QP at point P, then L is tangent to the circle Q. All right. Questions, comments, thoughts? Okay. All right, let's do a couple examples. This first one says ED is tangent to circle O. What's the value of X? So ED is tangent to circle O, which means that at point D, that's my point of tangency, this is a 90-degree angle. How do I find X? Anyone have any ideas? How do I find X? Jackson?
I don't know how you would find it. Or what? D would be 90 degrees.
Uh-huh.
Right.
Yep, D is 90 degrees. And so, yeah, I do have a little right triangle here. If I think of this as a right triangle, does that kind of help you figure out how I find X? What do I need to do?
You add 90 to 38, and then that would be 128, and then you do 180 minus 128.
Yep, very good. I'll set up a nice equation, but you can do some of that like in your head off to the side. I would think of it as like 90 plus 38 plus X equals 180. So 90 plus 38, 128, minus from 180, we get 53, 52. Awesome. Anybody questions yet? Okay, let's look at the next one. This one says, what is the radius of circle O? So radius are these two lines right here. They're both labeled X. And I know that this is tangent. I've got a little right angle right here. How can I find X? Anyone have any ideas? So kind of a big hint. We just spent the whole last couple chapters doing triangles because we're going to keep using triangles. Do you see a right triangle here as well? What's one of my sides? 10. What's the other one of my sides? It's not just 6. What'd you say? 6 plus X. And then what's the third side? X. I'm going to do Pythagorean theorem here to solve. I'm going to do 10 squared plus X squared equals X plus 6 squared. This whole side is not 6X, it's X plus 6 because I've got a part that's X and I've got a part that's 6 and I put them together to be X plus 6. And that's the hypotenuse because it's across from the right angle. Oh, sorry. So I have to do 10 squared plus X squared and that equals X plus 6 squared. So 10 squared is 100, X squared is just X squared. My biggest thing, you need to FOIL this X plus 6. You don't get to square X, you don't get to square 36. You have to FOIL it out. So I'm going to do it over here. I'm going to do, is that a hand? Okay, give me 1 second. X plus 6, X plus 6. And you have to make sure that you do X times X times 6, 6 times X, 6 times 6. Okay, so make sure that you FOIL it all the way out. And then get your answer. Oh, and that's going to be like the right side. So I get x squared plus 6x plus 6x plus 36. Oop, I lost an x. 6x plus 6x is 12x plus 36. So this goes on the right side of my equation. So 100 plus x squared equals x squared plus 12x plus 36. Everybody good so far? All right, start combining your like terms. So I'm going to minus x squared from both sides. Oh, shoot, that's going to cross my x squared out. That's actually really easy and really helpful for me. So now I just have an x all by itself. So let's minus 36 from both sides. And we're going to get 64 equals 12x. Divide by 12. That does not divide evenly because I know I did it an hour ago. So you can make it be, I think, 16 over 3. Or if you put in the calculator, it's 5.3 repeating. And so my x is 5.3 repeating. And that's all I need to do because I found the radius of the circle because the radius is x. That's it. Everybody good? All right, let's do another one. This one says, is ML tangent to circle N at L? Explain. Is this tangent to the circle? How do I know if it's tangent? What would be true if it was tangent? Caleb? Where? Where L is. If that was a true statement, there would be a 90-degree angle there. Does anyone remember how I can prove if that's a 90-degree angle? How can I prove this is a right triangle? What would have to be true if it was a right triangle? What like theorem have we used? That's yep. That's just to make sure it is a triangle.
A plus B squared is bigger than
Perfect. So what you're getting at is I want to use Pythagorean theorem, right? Remember to make your biggest side the C. So I want 25 to be my C. So I'm going to say, I'll even do the same thing as what we did all kind of last unit. I'll do 25 squared equals 7 squared plus 24 squared. Remember, C is across from my right angle, or 25 is across from my right angle. It's also the biggest side. So make sure you put 25 by itself or else you might get the wrong answer. And so 25 squared is 625. 7 squared is 49. And 24, I don't know that one off the top of my head, 576. We're kind of asking, like, is this true? Is this true? So now I'm going to add 49 to 576 to see if that's true. Y'all good? Okay. Where's your bag at? Okay. Okay, that's fine. All right. So 49 plus 576 is 625. And that's exactly what I want it to be. So 625, that's true, right? That's a true Pythagorean theorem. Both sides equal each other. So we're going to say, yes, it's tangent because it's a right angle. And when it's a right angle, then that means that line is tangent. It all kind of feeds into each other. Cool? Anybody questions yet? All right, let's look at the last one on this page. Okay. I've got ML and MN are tangent to circle O. Okay. If MN is tangent, what do I know? What can I write on this picture? That's what it should say. Caleb? Good. The angle at L is 90 degrees. And then what else do I know? N as well. Good. I think you said both. I just couldn't tell. All right. Why is that helpful? What is this going to help me do? Caleb? Yeah. Why? 4 sides. A 4-sided figure, its angles all add up to 360. Does anyone know specifically what kind of 4-sided figure this is? I believe this is a kite because the opposite angles are congruent. So in a kite, opposite angles are congruent, and these sides are congruent, and these sides are congruent. You don't know this fact yet, but I'll teach you that momentarily. So we've got a little kite there. So I'm going to add 90, 90, 117. I'm going to minus that from 360. Can someone do that for me? Add 90 plus 90 and 117. You got it. 297, and then we minus that from 360. What is it? Anyone know? 63. Okay, thank you. I was like, I'm sure somebody did it. 63. Awesome. All right, that's page 1. Way to go, guys. We're going to keep going. Ready to move on? Flip it over. Okay. All right, what I just prefaced, I'm about to teach you right now. There's a new theorem on the top of the next page. It says, if 2 segments from the same exterior point are tangent to a circle, then they are congruent. Okay, so we've got 2 segments from the same exterior point. So this point S, it's exterior because it's not inside the triangle, it's outside. And it makes a segment from T. ST is a segment that's tangent to the circle at point T. And then SR is a segment that's tangent to the circle at point R. So again, they share point S, and then they both have a point that's tangent to the circle. That means these segments are congruent. So if SR and ST are tangent to circle P, then that means SR segment is congruent to segment ST. Notice that I lost the arrows because I want to focus on just the segment. It has to end in order for this to be true. Okay. All right, questions yet? Comments yet? All right, let's do an example. This one says O is inscribed in triangle PQR, which has a perimeter of 88 centimeters. What's the length of QY? Have I used the word inscribed with you guys yet? No, inscribed means that it's inside of, and then it like is flush with, and by flush we mean like it touches, it's like connects at like one point where it can. So like X and Y and Z are all points on the circle, but are also points on the triangle. What we just learned, that word is tangent. They're tangent to the circle. And that's important to us. And then it has a perimeter of 88. I'm going to write that over here just so I don't forget. Okay. What we just learned a minute ago is if they share an exterior point and they have a point that's tangent to the circle, then those segments are congruent. So what is PZ going to be? What's PZ going to be? Not 17, 15. We want it to be 17 because you want to think about it being cut in half. But like if we were to look up here for PQ, that's definitely not cut in half, right? So it's the ones that are like make the little triangle. So this is 15. What about YR then? What's that going to be, Caleb? And then what about XY? Or sorry, let me rephrase that. We don't know what QX and QY are. So I'm going to use a little A to represent that. If we're going to do perimeter, you just got to add up all the sides. 15 plus 15 plus 17 plus 17 plus A plus A. plus 15 plus 15 plus 17 plus 17 plus A, and that equals my perimeter, which is 88. Can you solve that? All right, so 15 plus 15 plus 17 plus 17, I believe that's 64 plus 2A equals 88. Then I minus 64, and I believe I get 24. And then I divide by 2, and I get 12. So length of QA is 12. Does that look good to you? Everyone, any complaints? Nope. Okay. You all alive out there? Yep. Signs of life? Barely. Okay. I've only got 7 live kids in this class. Yikes. All right. Next one. Similar idea. What is SD going to be? What am I going to label SD? 3. What about RC? 3. What about BU? X, good. It's the guy next to him, X. And then what about TB? X, good. This time we have our perimeter is 18. Oh, they use the word circumscribed this time. It says the quadrilateral is circumscribed. That means it's around or outside of the circle. So inscribed means that that shape is inside the other shape. When it's circumscribed, it means it's about or outside the other shape. So the quadrilateral is on the outside, the circle's on the inside. So I'm going to say the perimeter is 18, and that equals what plus what plus what plus what? Looks like I've got a lot of the same thing. How many 3s do I have? 4. How many X's do I have? Good. Okay, easy. That makes it a little simpler. So 18 equals 4 times 3 plus 4 times X. So I get 18 equals 12 plus 4X. I'm going to minus 12 from both sides to get 6. And then I'm just going to divide by 4. You can think of it as 6 over 4, but it's most simple as 3 over 2. And you know I like fractions the best, but if you want to do a decimal, it's 1.5. And that equals X. All right, how are we doing? Okay, let's move on. All right, the next one says AB is tangent to C at point B, and AD is tangent to circle C at point D. Okay, if I know AD is tangent and AB is tangent, what do I know about segments AB and AD? They're congruent. Set them equal. X squared plus 24 equals 49. Minus 24 from both sides, and I get 25. Now I want to add something on this. So get everything, square root, all that stuff. Thank you. Okay, what I normally would tell you is that it's got to be positive 5 because we've got lengths of segments, and segments can always be positive lengths. I'm going to rephrase that for this and say that we could have a negative here. Does anyone know why I could also have a negative and it would be a legit answer? Why would it be okay if I plugged -5 into this for x? Caleb? Good. So I'm squaring the x. And so if I square a -5, it will still end up being positive 25. So that's why it's okay right here. I want you to think about it because sometimes it's really easy to be like, oh, there's no negatives. But like when I was making your guys' quiz for you, I had to work really hard to make sure that there were no negatives for x's because I didn't want you to freak out and be like, oh, well, we can't have that. You could have a negative x if when you plug it in, it turns out positive. So it's just at the end of the day, is the segment positive, is the angle positive, then you're fine. The x, it doesn't matter if it's positive or negative as long as the rest of the segment is positive. Cool? All right, we are going to finish this page. We'll just briefly talk about this bottom one, but I want to do one more theorem, and these are pretty simple. So let's keep on going through. It says, in the same circle or in two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So let's look at that. So the minor arcs, AB and BC, are congruent if and only if the chords, chord AB and chord BC, are congruent. So I can go both ways. If I know that the arcs are congruent, like what's marked here, then I can say, yes, AB and BC, those chords are congruent. I can also go backwards and say, okay, well, if I know chords AB and BC are congruent, then I also know that the arc lengths of AB and BC are congruent. Is that, you guys okay with that? All right, let's do a few examples with that. All right, so it says find measure of arc AB. Here's arc AB. I'm going to argue there's no math even to do here. It's just written in. Anyone know what arc AB is? Say again? 108. Why, Kate? Because they're congruent. Measure of arc AB is 108 because I know CD and AB, those chords are congruent. And that means that their arcs, CD and AB, must also be congruent. So measure of arc AB is 108. Very good. Let's look at the next one. It says in the figures, circle J is congruent to circle K, and MN is congruent to PQ. How do I find PQ? Melissa? We do set them equal to each other. So if the arcs are congruent, then that means the chords are congruent. So I'm going to say 2x plus 1 equals 3x minus 7 minus 2x from both sides. I also like to add 7 at the same time. You can do these in several steps. I'm just cleaning up. Oh, nice. And I got x equals 8. Before I move on to the next question, I do need to ask myself, did they want x or did they want a segment? Or do they want like a length of something? I think they wanted a length, right? They said find PQ. So what do I need to do to find PQ? 3 times 8 minus 7. Plug 8 into 3x minus 7. So 3 times 8 minus 7 is 24 minus 7, which I believe is 17. Always correct me if I'm wrong on my simple math, but I believe that's right. All right, one more like these. This one says, given circle P is congruent to circle Q. And it also tells me that this is 155. And it tells me that this arc is 205. Those aren't congruent. Oh, what do I get to do? I'm supposed to be congruent and they're not. Can I just not do anything? No, we can do a little search and find. Kate?
Would you subtract like 205 from 360? Because like the other side would be 155, right?
Right. So if Kate's like, okay, well, they're not congruent, but what if I found like this distance, the shorter one? Well, 360 minus 205 is in fact 155. So that means this is 155. And that also means this is 205. So the longer sides are congruent and the shorter sides are congruent. Oh, nice. And so now what am I able to do? Caleb? Good. Now I can set them equal to each other. So I do want you to think, just because it, like, we've done a bunch of problems where we set things equal, it doesn't mean you just automatically can. And we had to look at this. So it said 205 and then 155. So we had to double check, but we ended up just setting them equal. 7x minus 44 equals 3x. So minus my 3x, I get 4x, add 44, and then I divide by 4 and I get 11. Okay. All right, I am going to do this theorem really quick. We're not going to do any example problems because it's pretty self-explanatory, but let's look at this theorem. And then on Monday when we meet, we'll review this theorem and then do some example problems. The last theorem, the last thing I'm going to say today is that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so A, B, and C, D are only congruent if EG is congruent to EF. If those distances are the same, then I can say that CD and AB are congruent. You can also go vice versa. If I know that AB and CD are congruent, then I can know that EF and EG are also congruent. So that's all that's saying. I'm going to fill in this box. It says AB is congruent to CD if and only if EF is congruent to EG. So I'm just teeing that up for us to review and then practice on Monday. But we have done enough. Anybody have any questions on what we've done so far today? All right, I'm gonna have you get started on the homework. If you are doing it online, if you go to Schoology, I believe I put it as an assignment already. Sometimes I have it together and sometimes I don't. Oh yes, perfect. So circles day one, it's attached here. And if you want it by hand, I'm about to pass that out if you want a paper copy, okay? And we just learned really well today. So we're just gonna take the rest of the class and do that. Any complaints? He's like, that's fine. All right, let me stop my share. Let me stop my record.